Hello, my name is Ning. I work at Cisco Technologies. Today, I'm going to talk about enabling Secure Boot v2 on ESP32 platforms in development and in production. Before we start talking about Secure Boot, let me talk about myself briefly. I run the engineering team at a company called Cisco Technologies. For my background, I was trained in mathematics and cryptography. I have many years of experiences in building, attacking, and securing the hardware devices and key management systems in production systems. Currently, I work at Cisco to make hardware security easy for IoT device makers. Now let's talk about Secure Boot. Some of you may know the Secure Boot is the boot sequence of software images on the hardware device in which each software image is loaded and executed only when it's authorized by a previously authorized software image. So in the end, the authorization boils down to a root of trust in hardware. The Secure Boot needs chipset support. Our awesome ESP32 platforms support it. So once Secure Boot is enabled, it cannot be disabled on the same device. So it ensures that only signed firmware images can run on the hardware device. Therefore, it prevents the malware persistence at boot time. So depending on the design you're doing on the ESP32 platforms, so for example, if you are doing a hardware wallet using an ESP32, and you sell this product to your customers, you probably want to get Secure Boot enabled so that nobody can flash arbitrary firmware on your device. So to enable Secure Boot on the hardware device, usually the process is consisting of the following steps. So first of all, we need to create and management firmware assigning keys or a public key infrastructure. Second, we need to connect the just created keys to the hardware root of trust. So we need to do a field programming to configure security parameters and the root of trust into hardware. Then we need to properly sign firmware images, because once Secure Boot is enabled, all the images need to be signed in order to run on the device. So to sign a firmware image, we require signing infrastructures usually. So typically, a secure and easy to use signing key management it's not very easy to do. It's a challenge. We're going to talk about how we can address these challenges in the rest of the presentation. So now let's talk about ESP32. The ESP32 supports Secure Boot. So it's great that it supports this awesome hardware security feature. The preferred Secure Boot scheme for ESP32 platforms is the Secure Boot v2. Secure Boot v2 is available from ESP32 revision 3 and later. Also, it's available in the newer ESP32 platforms, including ESP32 S2, S3, etc. Secure Boot v2 is based on public key cryptography. It uses the 3K-bit RSA with the PSS padding to sign the bootloader image and the app image, and they will be verified at boot time by the boot ROM. ESP32 SPv2 supports at least two boot flows, which I call ESP IDF and MCU boot and Zephyr OS. Many of you are probably more familiar with the ESP IDF boot flow. It's based on ESP's IDF framework. So you can see that two boot flows in the slide. So in terms of the booting process, it's very similar. In the ESP IDF boot flow, the IDF bootloader is used. The boot ROM will load the IDF bootloader. The IDF bootloader will load the app image. In the MCU boot and Zephyr OS based boot flow, the boot ROM will load the MCU boot bootloader, and the MCU boot bootloader will load the Zephyr OS based app image. In terms of secure boot, there are some differences in implementation. In the ESP IDF case, the boot ROM verifies the IDF bootloader using a public key hash burned into eFuse. And the IDF bootloader will verify the FreeRTOS-based app image also using the public key hash burned into eFuse. In the ESP32 MCU boot and Zephyr OS case, the boot ROM will verify the MCU boot bootloader using the public cache in eFuse. However, when the MCU boot bootloader verifies the Zephyr OS based app image, it uses a public key embedded into the bootloader, the MCU boot bootloader itself, to do the verification. Conceptually, these two boot flows are very similar, but the implementations are slightly different. So how do we enable Secure Boot v2 on an ESP32 device? In general, there are a few things we need to do. First of all, we need to generate firmware signing keys. This is usually a one-time effort. Once the key is generated, it will be used to sign firmware that runs on the same device over and over again. Then we need to determine an eFuse configuration and blow the eFuses to get secure boot enabled. Again, this is a one-time effort. Once we know how to do it, we'll use the same configuration to fuse the same type of devices in the same product. Third, we need to sign firmware in order to have it run on the secure boot enabled device. So whenever we make a change in the firmware, we need to sign it again so that it can run on the device. So therefore, it's an ongoing effort to do firmware signing. Now let's talk about the signing key generation for Secure Boot v2 enablement. So for local development and testing, we can use OpenSSL or the ESP IDF tool, the ESP secure.py tool, to generate a key pair. And the key pair will be written into files. For production releases, file-based keys are usually not the best choices. We recommend to use a proper key management system, such as AWS KMS, GCP KMS, and hardware security module-based key management systems. In order to enable secure boot on the ESP32 device, we need to burn eFuses. We need to know which eFuses to burn. There are at least two ways of doing this. The first way is not the recommended way. We can burn the individual eFuse bits based on the values computed from the public key and the handpicked values to enable secure boot. Using the ESP eFuse tool, we don't recommend it because it's easy to make a mistake if we burn individual fuses. If we mess up with one bit, we may break a device. The recommended way for enabling secure boot is to sign the bootloader and the app image bundle with your choice of the private key. Then we flash the signed images and the valid partition table to an unfused ESP32 device. On the first boot, if everything works, if the images and the partition table are valid, the e-fields will be blown by the bootloader to get Secure Boot v2 enabled. So this is taken care of by the bootloader in one shot, and it only requires the flashing of the images. So that's the recommended way. So as I mentioned before, once Secure Boot v2 is enabled, only signed images can boot on the device. So we need signing continuously. Now, you probably have realized that the Secure Boot v2 enablement is largely a firmware signing problem and the key management problem. Because like once the firmware images are properly signed, it's a matter of like flashing onto the device to get Secure Boot enabled and to get the firmware run. So there are two cases we want to distinguish. The first one is the signing in development. Usually in development, we only play with a handful of devices. The signing key confidentiality is usually not very critical because these devices will not be used in the production scenario, will not be in the hands of the customers. So the signing process should be very easy to allow a fast iteration. So if there's a bug in the firmware, we want to be able to easily sign the firmware and get it run and test it on the development unit. For production signing, the situation can be a little different. If you are producing a design and you're selling the finished devices using ESP32, in many units, if you are selling thousands of devices to a customer, you probably don't want to get the signing key leaked so that an attacker can sign your firmware, can sign any firmware that runs on the device that you sell. So we should not expose the signing key in the production signing scenario. But still, like the signing process should be easy to allow fast releases. If there's a bug in the firmware, or if there's a new feature available in the firmware, you want to be able to quickly release the firmware. In both cases, it's desirable to have the production firmware very close to development firmware, so that what is tested in development can be reflected in production. So therefore, in terms of production images and the development images, ideally they should only differ only on public keys and signatures for Secure Boot enabled devices. Okay, so in the rest of the presentation, we are going to talk about how to sign firmware in development and in production to enable Secure Boot v2 for ESP32 platforms. So signing in development can be done in this way. So first, we generate file-based private signing keys using software tools like OpenSSL with the IDF tool. Then we use the menu config to enable Secure Boot v2. We will configure the signing key file in menu config, and also save the SDK config file for later use. Now we can use the ITF build command to build and sign an application with the saved SDK config. So we'll be signing a Void app. I'm going to talk about the Void app in the following slide. So once everything is signed, we can just flash the bootloader and the app image onto the device to get Secure Boot enabled on first boot. So development signing keys are usually not very security critical, and sometimes it's okay to check them into a version control system for easier access and for better backup. So here, like we are showing a couple of the important, like the most important configurations for enabling secure boot. From menu config. Usually, on secure boot enabled devices, we also recommend to disable JTAG, but enable secure ROM download mode on ESP32 S2 or S3, like when they are available, so that we can also flash the signed firmware onto the devices. Yeah, so once menu config is used to enable secure boot, we save the SDK config. Then we can use the SDK config to build Avoid app. So the Avoid app is an app that I wrote that the Thistle is open sourcing as well. So it's an app that does not do much. So you can see like there's only a few lines in the source code of the app. It essentially it prints out a message to the console. It does not do anything, but once it's signed, it can be flashed on an ESP32 chip to blow the security relevant bits to enable secure boot and other security features. A minimum fuse blower void app is very important in the production scenario because by doing nothing, it exposes no attack surface to a production device. So that's how you can assign firmware in development manually. And this process can be further automated into a one-click setup. So my company Thistle has released the developer tools, including a bunch of Docker files, the pre-built Docker images, and utility apps, including the Void app, to allow a one-click firmware signing in development. So here is the GitHub repo that we open source to allow this to happen. So firmware signing essentially becomes one command, one Docker build command, which you can see here. So you can override the SDK config and your private key as build arguments in Docker build. Now I'm going to show a video demo of development firmware signing using the Docker image. So first of all, we will clone the GitHub repo I just talked about. So once the repo is cloned, we change into the ESP32 directory and run the Docker build command. It'll take a few minutes. The Docker image is cached, so it's really fast in the demo. So these are the two build parameters that can be overridden to allow you to insert your own SDK config and your private key. So once the Docker image is built, the bootloader and the app images are signed automatically inside it. So we will activate the IDF environment so that we can flash the images onto the device. Now the IDF environment is activated, and the device is the device connected to the host machine running Docker. So that's ESP32. So now let's use the Void app. So before we flash the app, let's see what's happening on the board. Now things flash is totally erased. There's nothing on flash. Of course, we get invalid header. So that's normal. Now we are going to flash the signed bootloader image from the Docker container. Okay, the bootloader image is it's flashed onto the device. We're going to flash the partition table and the app image. Okay, now the Flash program is done. So let's see what's happening on the device. Okay, a good sign. We see this message. I'm the Void app. I do nothing. So the image has the app has booted. If we look more carefully, like we can see that the secure boot is also enabled. The from the console output, and this message is about the app image verification by the firmware bootloader. So we have secure boot enabled, and the signed images are up and running. That's a demo for doing development signing for ESP32. Now let's talk about the firmware signing in production. There are many reasons the file-based signing keys are not very suitable for production signing case. So we can't easily use the build system, the ESP32 build system, to load a private key from file system to sign a production image if you want to protect the key. The reason like file-based signing keys are not suitable is because they can be exposed by human beings or by malware. So some of you may still remember the recent firmware signing key leak from MSI. So we don't want to do that. We don't want to use file-based keys. Then what do we do? So we have a few requirements for signing firmware in production. On the security side, we want the production signing keys not to be exposed to any human operator or software. On the usability side, we still want the day-to-day signing operations to be smooth. So if every signing operation requires a ceremony to go to a safe to fetch a key, it's very inconvenient. So Thistle had a solution, based on a KMS backed the production signing keys. So essentially, we are providing a service, a firmware signing and patching service to use KMS protected keys. So the idea is that we manage the firmware signing key in the proper key management system. In this case, the key is generated in the system and also managed in the system. No one, including Thistle, has access to the keys, but the key management system can be used as an oracle to do the signing operations without leaking the private key. Conceptually, our idea is this: the input will be ESP32 firmware image, signed using the development signing method you saw earlier. Then this image will be uploaded to the service, will be sent to the service. The service will parse the image, extract the signature block. It will use the production signing key in KMS, in the key management system, to sign the payload, the content of the image, and replace the development signed signature block with the production signed signature block. So these two images will be almost identical, and the only difference is in the signature block. So that's the idea. That's how we propose to solve the problem. And in brief, we implemented a system, shown in this slide. So it's a firmware signing system, consisting a few microservices. So we have an IAM service to do user management, to do user management and access control, and also the signing configuration. The firmware patching service deals with parsing and patching firmware images. It has no access to cryptography related operations. For cryptography related operations, we have a code signing service, which will use a KMS. So our implementation is based on GCP KMS. So the code signing service will use the KMS, the managed production signing key, to sign a digest and produce the signature block. It will give the signature block to the firmware patching service to patch and get the a production signed image in the output bucket. So that's how it works. We don't get the signing key exposed to any entity outside of the KMS. So our ESP32 Secure Boot v2 production signing system supports both the ESP IDF boot flow and the IMCU boot Zephyr OS based Secure Boot flow. Now I'm going to show you a demo of doing production signing using the Thistle system. So in order for you to use the system, you just need to go to the Thistle website, sign up to get an account, then log in. Once you are logged in, you can create a project in which the firmware bundle will be uploaded. So we just call the project DevCon 23 demo, and it's for production signing of ESP32 firmware. Once you click the button of create Secure Boot signing key, a key pair will be created in the KMS. Now you can enter the project. Yeah, what happened here is that in the project you can upload your boot image and app image. There's a Secure Boot feature, and in settings you can also get the public key, for the key generated in KMS. Only the public key is available here, so you can use the key to do the verification independently if you wish. The private key is never exposed. Now let's go to the Secure Boot field and upload a firmware bundle. Yeah, we call it a dummy signed IDF firmware. So these firmware images are signed using the previously mentioned method in development. So let's upload the bootloader image and the app image. Once we click on the upload button, the backend will start processing these images, doing the signing and the patching, and put them to a place for you to download. Now the signing is done. These two production signed and patched images are available for you to download, and they are readily flashable to your unfused or Secure Boot enabled devices to enable Secure Boot. Okay, that's the end of my presentation. I'd like to thank Thistle Technologies for supporting this work, and also my colleagues at Thistle for their feedback. In particular, I'd like to thank Pierre for telling me about Expressive DevCon, and I'd like to thank Toru and Russell for helping build the production firmware signing service. This presentation can also be viewed from this link at the bottom of this slide. Thank you very much. Now I'm ready to take questions.